Okay, I think we can get started. It's 13:40. I know some people are still coming in, but yeah, I think we can get going. This is a very big room. When I first came in here, I legit considered running away for a few minutes. Also, the lights are very bright, so I can't see how many people are there, but I hope at least there is someone listening to talk, and I assume you're all here because you want to learn a bit about the principles and practices of building machine learning systems, or also known as what people tell us to build and then how we actually set it on fire in production. So who am I? I work as a machine learning engineer at Storytel. For those of you who don't know Storytel, we're one of the largest audiobook and ebook streaming providers in the Nordics. And I work on the machine learning team where we try to build recommender systems to help and delight users in discovering new content that they might enjoy. So why am I here doing this talk? Well, I joined Storytel last year, and one of my main missions was to try and start improving the machine learning platform and the machine learning systems that were currently in place at Storytel. And as you all probably know, it's 2023, and we've been living in this world where we have MLOps and we have DevOps and we have a ton of different frameworks for machine learning. We have programming languages, we have SaaS products, we have companies, we basically have everything. So this should really be a solved problem, and all I have to do as a machine learning engineer is click on the start button on a few products, and then it's all fine and it works. And this talk was really born out of a frustration with the gap between how many tools and frameworks and various kinds of systems we have for building machine learning platforms, and how hard it still remains in production to get something that's not on fire all the time. So when I say machine learning ecosystem, this is pretty much what I'm talking about. This is a picture from the Linux Foundation, and specifically the AI and Data Sub-Foundation, I guess, which attempts to document and catalog the vast ecosystem of various machine learning and MLOps tools that are available out there. So if you just look at this, you might say oh my goodness, you just pick 10 from this and then you just click start and then you're done. But as it turns out, and as I quickly discovered when sort of trying to build a machine learning platform, is that we are drowning in MLOps tools. I mean, literally, it's really hard when you look at something like this to even know, what do I get started with first? So we're literally drowning in these tools, but at the same time, we're kind of starving for knowledge on how to actually build something that works. And this stressed anonymous ML engineer may or may not be me. We will never know. But anyway, on the other hand, you might also ask, are machine learning systems really so complicated and difficult that we need a whole new ops discipline to build them? Or are we just kind of falling for the marketing hype FOMO that is propagated by some of the companies that are part of this ecosystem? So is it really that machine learning systems are so special that we need all of these tools, or does it all just boil down to good software engineering with maybe a few additional machine learning bells and whistles for the parts that are special to machine learning systems? And we're going to kind of take a look at what those parts are a bit later in the talk. But this is definitely a viewpoint that's also kind of interesting to consider. And one tweet that regularly keeps me up at night is this one from Jo Christian Bergum, who is a distinguished engineer at Yahoo and building the Vespa search engine, where he says basically MLOps was a mistake and we don't really need all of these massive amounts of tools and ecosystems because we already know how to build software. And just because one part of this software system is now a machine learning model that has learned some parameters from data, we really don't need all of that stuff. And part of me kind of wants to agree with him, because when I think of building difficult software, I think of this. This is Margaret Hamilton building the control systems for the Apollo lunar mission. Or I think about this. This is the Rosetta mission that that the European Space Agency launched a few years ago to explore what was happening on this comet. And if I think about what these engineers that were working on the Rosetta had to do, they developed their code, and then they only got to test if their code actually works in production 10 years later, because that's how long it took for this spacecraft to actually reach this comet. So when I think about my own code, sometimes I write code, and like 2 weeks later, I have no idea what it does anymore. Having your code be tested only 10 years after you've written it and still have it work after it has flown through 10 years of space travel with all the radiation and all the complication that can lead to is kind of amazing. So when I think about building hard systems, this is what I think about, and not necessarily like machine learning models. Because if we really think about it, people have been doing machine learning with Excel for decades and have somehow been fine. So are we really building something that special in machine learning, or are we just complicating things because we're engineers and our job is to engineer and sometimes over-engineer stuff? So these are the kind of things that I want to talk about in this talk. So first I want to take a look at what is a machine learning system and what does kind of MLOps best practices tell us on how you should build a machine learning system. And then I want to take a look at what actually happens in production. What lessons can we learn from setting these systems on fire? Do we need to automate or do we not need to automate? So hopefully this will be both fun and illuminating, and maybe you can laugh at some of the mistakes that I've done when trying to put machine learning systems in production. So first, let's talk about the principles. How do we build a machine learning system? Or, like, before we even get to that, what is even a machine learning system anyway? So chances are, if you talk to 100 different machine learning engineers, you will get 100 different answers. Because ultimately, every company has their own machine learning systems that are specifically developed to solve their business use case. And so there isn't kind of a one template fits all. And I guess if you really wanted to try and come up with some kind of answer for this, you could start with asking, like, okay, what is machine learning? Well, machine learning is the process of building something that learns from data, that improves continuously as it sees more and more data. Basically a machine learning model. Well, then by extension from that definition, you could say, okay, well, then a machine learning system must be all of the support structure and all of the chaotic processes and systems that you can develop around deploying, training, evaluating, and monitoring this software artifact that you get that learns from data and then can make predictions on data that it hasn't seen before. So let's make this a bit more concrete. So suppose you are a data scientist and you are working for a cybersecurity company, and you've said, okay, well, you know what? Malware is really difficult to detect with rules. Why don't we come up with a machine learning model that can detect a malware from some statistical properties? So you start building, you're working on your own, you start building out this little system. You have some storage layer. These are images that are specific to Google Cloud because that's the platform that I'm most familiar, but you can imagine this could be any generic storage layer. In this storage layer, you have collected some samples of malware and some samples of normal programs. Then you compute some features that you might think are useful for the model to learn to distinguish between malware samples and normal computer programs. You store them in some kind of data store, and then you come up with a little data pipeline. So at this point, when things are still very simple, this data pipeline can be something as simple as a sequence of Python scripts. And all these scripts do is they read from this data store, they split the data into a training data set. So this is the set that you will be using to teach your model to distinguish between malicious and benign computer programs, and then a testing set. And this is the set that you will use to check how well the model has learned. And obviously, it's important for you to separate these because you want to check that the model hasn't memorized the samples that you were showing it, because then it would be useless when you put it in production. And so that's what the test set is for. And then you have a number of other steps, and you come up with this little data pipeline. So everything is still kind of simple and especially if you're the lone data scientist in this fictional cybersecurity company, you can probably get away with some Python scripts and maybe a few cron jobs. And at the end of this process, you produce a model. And your manager says, okay, really cool. You have developed this model. We want to put it live. We have an upstream API or an upstream service that's going to be sending, collecting some samples that people submit. And we need your model to tell whether or not this particular computer program is malicious. So you wrap this model in a little API. This is what we call live inference. And then you wait for requests to come in. And you get a request for the model to make a prediction. And the model does its job. So it says, with very high probability, this sample that was sent to me is malicious. And up until this point, everything works fine. But then things start to get a bit more complicated. So the one special thing, perhaps, that distinguishes machine learning systems more than from normal software systems is that the inputs are not in your control. And what I mean by this is that what kinds of malware samples you get can change very rapidly. So today, your model is an expert on determining whether or not something is malicious based on all of the data that you have collected up until day one. But tomorrow, people may develop a new type of malware. And now with all of these automated exploit creation toolkits, we know that we can get ChatGPT to help us write malware. The rate at which these malicious samples change can be very fast. So on day one, your model might be performing very well, but then on day two, when you get some new kinds of malware samples that are sent to the model to make predictions, it might not be so great anymore. So you see this probability number is starting to decline. The model is becoming less and less confident at making predictions because it is now seeing samples where the data of those samples is very far or starting to get further and further from the distribution of the data on which the model was trained. This is something that we talk about a lot when building machine learning systems, and we usually call it a data drift. So on day two, things were getting worse, but they are still kind of okay. And then, on day three, as the malware samples that you're starting to see are kind of drifting further and further apart from the training data on which the model was trained, you're starting to see kind of catastrophic degradation. So by day three, or maybe day four, when you send a malicious sample and try to have this model make a prediction, all of a sudden the model thinks that this sample, which we know is malware, is actually benign because the probability has dipped quite low. So at this point, you would be already seeing catastrophic degradation of model performance. So this is one challenge. And to combat this, you basically need to put in monitoring. You need to keep tabs on what this model is doing in production all the time to make sure that it doesn't drift too far away from what it's supposed to be doing. You need to make sure that if you are trying to predict whether or not something is malicious, that even X days after the model has been trained, you're still having some kind of acceptable performance. And this is not always as simple of a problem as it sounds, because obviously, in order to measure how well your model is performing, you need data where you know the ground truth. So in order to compare the model's responses to the actual values, you need to collect some well-known data samples where someone else has done the labeling. Now, with malware, this is still possible because we have a lot of malware repositories where researchers are submitting samples, so we can kind of take data from there and continuously test our model. But with something like recommender systems, you might not even know kind of what the right answer is. Say we're trying to recommend music to users or podcasts to users. If a user clicked on that podcast, does it mean that they liked it? Does it mean that they, were just viewing it? It can be hard to tell what is actually ground truth in many cases, which makes this model monitoring quite hard in some cases. Now, suppose you've noticed that, okay, your model has degraded, so now you need to retrain a model. So in your little machine learning system, you do what I'm sure we all have done once or twice when saving Word documents. Instead of like numbering them properly, you just say like model 2, and then you realize you need to change something. So you're like, okay, I'm going to call this file model 2 final, and then you have final. And I know that I've done this a lot. But the more you start doing this, the harder it obviously becomes to keep track of like, okay, when exactly was model 2 final trained? What data was in model 2 final? And so eventually this kind of goes out of control. So the second part that you need to try and manage this is some kind of system to do model versioning. It doesn't have to be complicated, but it's definitely a key part of building something that is functional. Now, suppose you start adding more and more data scientists to this fictional cybersecurity machine learning team. Now, all of a sudden, you don't just have one model, you might have 2 or 3 models, or in some bigger companies, you might even have 80 models or 100 models, and each of these models needs a unique data pipeline to train it. So now, all of a sudden, the original system that this fictional cybersecurity machine learning company developed, where each of these data pipelines is like a sequence of Python scripts and it runs with cron jobs, that is no longer manageable because it's just a chaotic mess. So you need something to do orchestration, making sure that these pipelines are scheduled to run on specific intervals, that there are enough compute resources for all of them, that they don't collide. So basically this. Then you might also be faced with actually trying to determine which of the 2 models is better for something that is more of a long-term effect. So if you're, say you're trying to recommend podcasts to users and you're trying to see if this actually makes the users more happy with your platform. In this case, you might need to run 2 versions of the same model side by side for maybe a few weeks and kind of split your users into different groups and then try to collect statistics on various signals to see which model performed better. So A/B testing or online testing is another component that you might add. Then, okay, now you're seeing that what started out as a simple sequence of Python scripts that were running on someone's Linux machine and a simple API is starting to get more complicated. So this, I guess, is where you might be starting to see why the whole field of MLOps emerged, because there are a lot of moving parts here. So now someone says to you, okay, we're providing a live service, we need to make it go faster. Every time I ping this model API, it takes 25 milliseconds for it to return a prediction, and that's too long because my users get impatient and they rage quit the website or whatever, and I need it to go faster. So you need something that does model optimizations. In addition to that, now your data scientists are saying, okay, well, developing these data pipelines takes very long, but part of the kind of challenge in machine learning is that you need to iterate usually many times on a model before you get something that has good performance. So we need some kind of system that doesn't touch this production system, where we can make experiments and try to tune hyperparameters, try different data sets, and we need that to kind of be separate from that. So now, in addition to all of this production complexity, you kind of need to maintain this parallel system where data scientists can use whatever tools they need to perform different kinds of experiments. And in this illustration, I'm using Jupyter Notebooks. It's a type of visual programming environment, or IDE for data science, if you will, that people commonly use, but that is very hard to put into production. So these kinds of 2 systems have to be kept separate. So now, in addition to this production mess that is already starting to look quite chaotic, you also have this other system that is also producing models. And you need to kind of manage how these models transition from the experimentation part, where data scientists are making changes, tuning hyperparameters. How does it actually go from that environment into the production environment without causing complete chaos? So we're already seeing that what started out as a fairly simple problem and what is still kind of a fairly simple system is already starting to have what we call exponentially increasing complexity. So we have these various systems that we need to make sure that the model is functional in production, and then at the same time, all of these systems have to somehow communicate with each other, and so we're starting to approach chaotic levels of mess. Now you take this and you add to the mix your standard software engineering bad practices that can be quite common in many machine learning teams, like no version control. People maybe are not used to using Git or another tool. They don't want to use it. Lack of testing, lots of copy pasting code. There is extreme coupling between all of these components, or they're kind of hard-coded parameters, or there's a specific API and we need to adhere to that. It's hard to create integration tests when you have all of this going on. And basically, you very quickly get this. So it can be quite chaotic. So I guess this is part of the reason why this whole field of MLOps came to be, is because people were building these systems in production and seeing that you start from something very simple, and you think like, okay, I can manage this. This is just a Python script. But then when you start adding even small amounts of complexity, the resulting overall coupling between the various components just increases exponentially. And all of a sudden, you have so many moving wheels in your system that you don't even know what's going on. So I think that is definitely part of the reason why people started talking about MLOps. And I went into the literature and I wanted to see where was this concept of we need some kind of ops discipline for machine learning actually born. And what the internet tells me is that the first kind of inklings of this came from this paper by Google that basically details exactly this phenomenon that I just showed you on the preceding slides, that seemingly simple systems very quickly accumulate lots of tech debt and become unmaintainable. And so what they talk about in this paper is why machine learning systems really quickly become hard. Well, first of all, it can be very difficult to test end-to-end when you have so many different components and you need expensive integration tests, which are both difficult to write and also take a long time to run. Many machine learning models produce non-deterministic outputs, which makes it really hard to unit test them. You need lots of glue code to glue all the various parts of the systems together, and you need someone to maintain this glue code. In addition, many pipelines have complicated interdependencies. For example, one pipeline may depend on another to finish before it was running, or it may depend on some tables that are only available at certain times. And so all of this results in various, what they call pipeline jungles. In addition to this paper, if you're moving in the kind of MLOps circles, you will often hear this statistic cited, that the reason that we need MLOps and that the reason we need all of these tools is that 80% of machine learning projects that companies attempt never make it to production. So when I saw this statistic, and there are, by the way, different versions of this. Some people say it's 54%, which is like an oddly specific number. But yeah, there are different versions of this number floating around. And I wanted to dig in and find out, like, how was this number really calculated? Because I was quite skeptical about this. And basically, this number kind of leads back to this article by a magazine called VentureBeat, which, by the way, is a sponsored article. I don't know if that makes it more or less trustworthy, but there was this article from VentureBeat that asked, why do 87% of data science projects never make it into production? And I assume that they kind of put together this article to justify why some of the MLOps system existed, but that's an interesting number nonetheless. So given that we have this kind of statistic that a lot of businesses fail to put their machine learning projects into production, it's probably no surprise that, you know, a lot of companies have sprung up to try and plug this gap and make a ton of money at the same time. So there is definitely some sort of business opportunity in helping to solve these complexities. But definitely as a machine learning engineer, just looking at this is overwhelming. So one of the experts in this field is Chip Huyen, the founder and the CEO of Claypot AI, a machine learning company. And Chip has written a lot of publications about this ecosystem and looked at the various tools. And she has kind of produced a taxonomy. So Some of these tools are specifically optimized for monitoring. Others do model optimization. Some of these are all-in-one. Some of these are only for orchestration. Some of these are only for data cleaning and validation. Others are for model registry. Some are for experiment tracking. And the list goes on and on. So even though this is quite overwhelming, you might say, OK, we have all these tools and frameworks. We know that building machine learning systems is chaotic. But given that we have all of these tools, surely we should be able to still do this. But then what actually happens in practice? This is where I'm diving into the second part of this talk. This is what actually happens when you try to build a machine learning platform. And this is a collection of 10 lessons that I have learned during the past few months of actually trying to put some of these principles and practices from MLOps into production. So first lesson should probably come as no surprise to anyone. Tools alone won't save us. I'm sure you've all heard of this before, but just because you can add a tool doesn't mean that your system is suddenly simple. And for those of us who were around, I think in 2017, when Kubernetes was first gaining speed, you might remember that there was a similar sentiment that all of your deployment worries will disappear once you start deploying your apps on Kubernetes. Well, the truth is more or less that, well, you deploy something on Kubernetes, and now you have two problems, your app and Kubernetes. So when I saw this tweet, I thought that was quite funny, because this is an NLP researcher who was saying that building an end-to-end MLOps platform would definitely be a billion-dollar business, and people were replying to him saying, well, we already have a ton of MLOps companies that are million-dollar businesses. And then what the conclusion was that the existing services are so hard to use and combine. And I fully agree with this, that we often fall into the trap of thinking that, well, we have this tool, why don't we, like, it will solve all of our problems. But the reality is much more complicated than that. So imagine if you have this, which is our little complicated software system, and now you just add 3 tools. Job done, we can all go home. Well, no, not really, because all of these problems are still your problems, and now you've also added 3 potentially unknown sources of problems. I think part of the reason that we are so kind of easily attached to just using some tool or machine learning framework or open source product to kind of fix our problems is that a lot of these trends in MLOps and building machine learning systems come from big tech companies. And we're all surrounded constantly by this information that is coming out of them, that it can be quite hard to resist the fear of missing out because you're not using the latest and greatest machine learning framework. And just as a few examples, if you follow any of these big tech companies, you'll see a constant stream of blog posts that are being published. Spotify is innovating with Ray, which is a distributed computing system. Uber has developed Michelangelo. Okay, this is from a few years back, but this was big news at the time. Shopify has developed Merlin, a new machine learning platform. And when you're surrounded by all of this information coming out of big tech companies, it's very easy to fall into the trap of thinking that, you know, we are like a big tech company, we should be doing what they are doing, when in fact, we might not even have the same problems that they are having. We might not have the same motivations that they are having. And while, yeah, there is cool tech that they're using, and we might be using boring tech, but at least boring infrastructure will not wake you up in the middle of the night because of some configuration issue. It doesn't generate cool blog posts, but it has known unknowns. And this, I think, has been kind of a principle that people have been talking about in the infra world for years, is that infrastructure should ultimately be boring. It should be so boring that you don't even know it's there. And it should definitely not have unknown unknowns, because those are the ones that are going to be waking you up at 2 a.m. at night because of some issue that you will then have to debug. And this is basically why just adding tools to your machine learning system is not necessarily a good recipe, because for every cool piece of tech that you've seen Shopify using, you've seen Spotify using, there are exponentially multiplying unknowns. So these are failure modes that you don't know existed, and maybe no one knows that existed because this technology is so new. And so imagine, now you already have this pretty complex situation going on. You add these three to the mix, well, now you have 10 more problems, potentially. And I think we're kind of seeing this overcomplication and kind of obsession with tools now with vector databases, which are some components that we can sometimes use in a machine learning system to store embeddings, which is just a type of representing data. So there are now lots of companies that are providing vector databases. There's Pinecone, there's Quadrant, there's a bunch of these. And so someone was asking on Twitter, like, which one of these would you use? And the answer was by Eugene was none. I would just use a simple array. And I think this is the energy that we should all probably be bringing a little bit more into building machine learning systems, is to not saddle ourselves with the complexity of scale until you actually reach that scale. A lot of these systems used by big tech companies are specifically developed to answer their needs. And if you don't have 1 million active users that are, using your site constantly day in and night, then perhaps you don't need a fancy vector database because you're not hitting that scale. So why would you give yourself a headache of managing something that is created for scale when you don't have that? The hardest problem is not the tech. So I think this is a common theme that probably reverberates in other parts of software engineering, but very commonly the hardest problem of building a platform is not the tech. It's the fact that there are kind of two engineering cultures in machine learning. There is the data science side, where people can come from a variety of backgrounds, from academia, from industry, from natural science research, and then there is the engineering part that mostly comes from kind of a software development background. And what I like about this blog post that was published by Google is that they actually talk about how a German steel distributor, Klöckner, reinvented its data science workflows, and they mention very many times during this blog post that the hardest problems that they were facing were actually not so much the software tools that they were using for their machine learning system, but it was that there was a really big gap between the DevOps engineers that were in charge of deploying the machine learning model and the data scientists that were developing this model. And so some of the cultural kind of challenges that they mention was, like, for example, advocating for version control. The DevOps engineers wanted everything to be in Git. The data scientists were not so sure. The data scientists wanted to maintain their own virtual machines. The DevOps engineers thought that this was both a security and an infrastructure nightmare. And so bridging the gap between these two cultures is one of the problems that you can't solve just by deploying some MLOps tool. To take it even further, these problems also exist even in big tech companies where you might think that there is a pretty strong drive to have excellent engineering culture. And this is another paper that was published by Google that attempts to create some kind of framework for you to use to evaluate your production readiness. And there is an interesting point in this paper that says that even though Google has a pretty rigorous engineering culture, these tests that they suggest in this paper were not implemented by more than 80% of teams. And I thought that this was a pretty interesting statistic, given that we often think, like, well, in places like Google, there is a pretty hardcore engineering culture. So probably, they don't have this problem of having a big gap between the engineering side and the data science side. But it turns out that even at places like Google, this does seem to be a problem. Another thing that kind of follows on from this is that automation is not necessarily a silver bullet. So as engineers, I guess one of our professional hazards is that since we know how to program and we can write scripts and services, whenever we see a problem, even if we have to perform it only once, we really want to automate it away. And this kind of desire to automate things doesn't necessarily exist on the data science side, where people are more interested in doing experiments and kind of having the freedom to tinker. So when you're building a machine learning system, as an engineer, your first instinct is to automate everything. Just slap in CI/CD pipelines, automated unit tests, automated integration tests. Make everything work with a click of a button so that no one has to use their personal VMs or scripts. Now, the thing about this lesson is that every layer of automation you add is great when it works. So say you've onboarded your machine learning system to use GitHub Actions. It's great when it works. But every extra layer of automation you add is one extra layer you need to debug when it doesn't. So now say you've added GitHub Actions to your machine learning system. Well, when it works, no one cares about it. But the second that it breaks, you realize that you now have a dependency on something else. So definitely, yes, you need to automate things where it makes sense, but you also need to be mindful that every extra layer of automation you add is something that someone will need to debug when it eventually breaks down. Lesson 5. Simple models exist only in theory. So one of my favorite things about reading many of these MLOps tools documentations is that they all start with this simple story of how we developed a machine learning model. So we have some data, we make a simple pipeline, and out comes this very neat little file that is our model, and then we can upload it somewhere, we can version control it, we can perform various things on it. This is how all the documentation starts. Now, when I look at this very neat and theoretical view and I take a look at the production system, I'm quickly faced with this. So in production, often your data can be spread across multiple different databases. There can be a random storage bucket. You can have some GDPR requirements, which means that part of your data maybe lives in another project. Then you have a lot of SQL statements that were developed under perhaps intense pressure to ship something. You have some random Python script that reads from some random Excel sheet that someone who no longer is at the company has developed. And then all of this gets uploaded into a massive kitchen sink Docker container, and perhaps you don't ever even output a model file. You just train the model, you make predictions, and then you write something out to a SQL table. And so when you're trying to apply one of these model versioning tools, you read the documentation and they say, okay, well, just take, you have a simple pipeline, just take the file that comes out of it, upload it to our tool, and we'll do the versioning. And you're staring at your SQL statement, random Excel sheet file, and Docker container, and you're thinking like, well, my reality is like exists in a different universe than what this tool suggests. Yeah. So these tools are developed for very specific models and sometimes reality, where we have various pressures, such as pressures from the business, to deliver things that doesn't correspond to what the tool was meant to do. So this is perhaps a bit of a controversial one, but lesson 6 is that abstractions make you go fast and slow you down. And so what I mean by this is that in machine learning engineering and data science in 2023, we're spoiled for choice when it comes to various high-level frameworks and libraries that we have to do for model training. And all this boils down is that you get used to just saying, okay, model.train, and then ignoring everything else that has to happen under the hood for this model to actually train. But if you think about it, there is actually a huge amount of complexity that goes on behind this API call. There can be data that is being loaded from a database into your Python process. There might be API calls to create a pod on Kubernetes. There may be all kinds of things. And so we have developed these abstractions so that we can develop faster. But then when we kind of start hitting scale and we need to debug why something isn't running fast, then these abstractions hurt us because we're used to just saying, okay, model.train, and then we don't know why it's so slow. So there is a constant tension when you're developing these systems between adding more abstractions and increasing the velocity at which data scientists, at which the humans that are working in your ML system can work, and the tension between bringing things closer to the metal or to the data, but making things slower to develop. And you have to find the suitable trade-off for your particular case on how to kind of balance this. Lesson 7 is more of an observation, but another thing that makes machine learning systems hard in production is that your feedback loops can vary from seconds to weeks. Now, if you think about standard software engineering, you usually can set up your developer tools in such a way that you can have almost instant feedback on how your code is doing. So you can have unit tests, integration tests, CI/CD pipelines, and there is a good chance that within 5 minutes of you making a commit or opening a pull request on GitHub, you will know, at least to a certain degree, whether your tests have passed and whether your linting is okay and various things like that. The problem is that in machine learning systems, some of these feedback loops can take many hours. For example, if you make a commit, you open a pull request, and you start a model training process. Well, it can take anywhere from 1 hour to 48 hours for the model to finish training, and only then you'll find out if your change was good. Then if we take it a bit further, if we're thinking about monitoring, it can be weeks between you actually making that commit into your production repository and you finding out that your model, say, degrades really quickly in production. So you have to try and understand why. If we're talking about A/B testing, it can even be months between you making that change in production and you finding out that something was not wrong. So when you're trying to design these systems, you have to think, how can I track this change across all of these different cycles to then, if something goes wrong, say at the A/B testing stage, to try and understand what were the changes that I made that then caused this thing to go wrong. Okay, lesson 8. The various machine learning frameworks that we have tend to encourage coupling with the underlying infrastructure. Now, what do I mean by this? Well, if you recall before, I mentioned that when we're building models, we often need data pipelines. So these are basically just sequences of steps that have to run in a sequence to do various transformations on the data to produce the final model. Well, a lot of the frameworks that we have in machine learning have specific SDKs, which means that when you're specifying this model, you have to write your code in a very specific way. So this is kind of pseudocode or pseudo Python code, but basically what this shows is that for every framework that you use, you have to import a specific library. And that library is kind of tightly coupled on the underlying infrastructure that the pipeline will then be deployed on. Now, this is all fine and okay if you're just specifying your pipeline once. But say you are using Airflow and all of a sudden, your tech leadership tells you that, well, we don't want to use Airflow anymore, so we have to migrate everything to Vertex AI or another service. Then now, all of a sudden, you have these pipelines and you have this logic that is tightly coupled with Airflow. And you can't just pick up and move, you have to rewrite it. So that is another problem, is finding a way to develop your actual pipeline machine learning logic in such a way that it's not too tightly coupled with whatever framework you happen to be using. It's not always, of course, possible, but at least you should strive towards it. Lesson 9. Different parts of your system will need different development velocities. Now, remember, a few slides back, we were talking about these two layers in a machine learning system. So we have the production pipelines that produce the models, and then we have the whole experimentation setup where data scientists are trying to develop new models or experimenting with various parameters and so forth. And so you have to account for the fact that in this experimentation layer, you should do everything you can to make sure that iteration velocity is high. So that might mean that you don't have CI/CD pipelines at this level. You don't have unit testing. You expect that most of the code that data scientists write at the experimentation stage will be thrown away at another point. Whereas when you move to the production layer, you lower the iteration velocity, because here the consequences of making a mistake are, of course, much larger than if that happens at the experimentation level. So you have to design your system with this in mind, that there will be different layers of the system where people will need to iterate at different velocities. And then finally, what is kind of the most important gap to close if you want to be able to quickly develop machine learning systems is this experimentation production gap. So how do we make sure that the code that is developed in these Jupyter notebooks, the models that are trained here, how do we make sure that they can go as quickly as possible into the production pipeline? And at the moment, there is really no good solution, at least that I've been able to find, that does not involve copy-pasting code. I know that there are some companies where people run Jupyter notebooks in production, but there are various kind of risks and difficulties associated with that. So if you don't get this right, if you make it very hard for people to move their code from experimentation to production, it might take weeks or even months for you to get a model that was developed in the experimentation stage to production. And that is, of course, bad because there is a chance that by the time you actually get it in production, perhaps the model is no longer relevant. All right. Well, the disappointing, maybe, answer to all of this and to MLOps is that it does indeed look like most of the knowledge or the challenges that have to do with building good machine learning systems boil down to just plain good old software engineering. And there is a quote that I like from a Google researcher, Martin Zinkovich, that says, "Do machine learning like the great engineer you are, not like the great machine learning expert you are." And this very much matches all of the things that I've observed trying to build these systems, is that a lot of the problems are actually engineering problems, and that just because we have thousands of MLOps tools and frameworks doesn't mean that those problems suddenly go away. In fact, they might even multiply if you start adding tools to the mixture without carefully considering why you need those tools or if you need them at all. All right, so this is the end of my talk, and any questions or comments? Stunned silence. Okay, you can rage tweet at me if you want to give me your feedback privately.